Will share my screen, and if you can confirm if you can see my screen, you can. Brilliant. Good afternoon, and thank you for joining this session. And I would like to really express my appreciation for the OCP team for allowing us to come in here. I know it wasn't an easy one because normally you deal with system level items, while in this instance here, it's a deep dive into component level. And I'm hoping to be able to give an appreciation of the role it plays in the upper system level. So the topic is SuperSOA MOSFETs for HotSwap server application. My name is Sami Ould Ahmed. I'm a senior application engineer based in Manchester, working for NextPeria. So you have to forgive me for not doing a video call. It's 10 o'clock in the evening here, and it's not a sight you would like to see. I shall be as brief as I can because I've got a few slides to go through, and hopefully it'll give you an insight on the actual component and how it the importance it has on the server application. The MOSFETs are pretty much used in anything that has a name electronics in it. The session today will focus particularly on MOSFETs destined for this kind of application, what we call non-stop application, cloud computing, network storage, HotSwap servers, and so on. The list goes on. The one that we will be focusing on today will be the HotSwap systems. And for the ones that are not familiar with the term HotSwap, we'll give an explanation to that. Now, the simplified circuit that represent a server board is done in this slide here. The way the actual board is seen by the module is a big capacitor resistor kind of network. Now, as I said, this is a simplistic model representing the server boards. Normally, the server boards are powered through a same power supply module, and cards are plugged in and pulled out where there is a need for upgrades or capacity adjustment or simply maintenance or failures. Now, these swapping of cards is what we refer to as the hot swap. During this hot swap, it is very critical that the rest of the servers are not interrupted and communication carries on. Now, what happens when you plug in a new board? That new board is initially discharged, and the insertion of that board will result in a very large amount of current, the inrush current. That potentially can cause damage to the boards or to the rest of the system. Best case, if it doesn't cause any damage, then it will have issues such as connector sparks, backplane, supply glitches, and card reset, which is something that, with all the data, the importance of data going on, cannot take place. You know, the continuation of the operation is important. Now, the solution to that is that the power supply module has to deal or has to be designed to cater for a hot swap. And the way it's done is through an IC controller in the module that will have the control over the current or the amount of current that is being supplied to the rest of the boards in the system. The way it does that is it has this is again simplistic representation of the module, where it have an IC driver and it has a MOSFET that it controls. It has also a sensor resistor that the desired current is chosen specifically for the particular load. The designer will choose what that current is depending on the load it's trying to drive. And as such, it will drive the MOSFET in a soft start where the actual current is controlled. A MOSFET is a switch, and it is a very fast switch. If you switch it on as it's normally switched on with its speed, we're talking nanoseconds, then that inrush current will cause damage. The way it's done here is that the controller will sense the current and it will adjust that switching very softly to allow for that just specific current to go through in a safe manner. Again, the solution, as I said, is the controller with the MOSFET. And if you pay attention to the position of the MOSFET here, it actually sits between the input supply and the load. Just goes to show the importance of this position as a bridge between the supply and the rest of the loads. Now, the solution, as I said, is a controller that uses a MOSFET. Now, can it be in a MOSFET? Not quite. The MOSFET that it has to use has to have a very strong, what we call SOA, a linear mode operation. I will explain again what this linear mode means. It's basically the MOSFET being used as a voltage control resistor. So you put it into a very high resistor type of electronic device where you control the current. So the strong linear mode performance is key to the MOSFET. Now, what does linear mode means? Linear mode occurs pretty much every time the MOSFET goes through a switching transition. Now, this is a representation of what happens in the switching transition of the MOSFET. What we have, I need to get the pointer. So what we have initially when the MOSFET is off, it's represented by the VGS. The MOSFET is turned on by applying a voltage between the gate and source. So initially that voltage is 0 or minus. The MOSFET is turned off. The full VDS stands for drain and source. So the voltage across the MOSFET is at its highest. And as the gate source voltage is applied to the MOSFET, then the MOSFET starts turning on. And as such, the current through the MOSFET will start flowing. And the drain source voltage will drop. In this transition here, the MOSFET is in its linear mode. Now, normally this happens in nanoseconds. We're talking 50 to perhaps 80 nanoseconds. In linear mode, specifically designed for soft start, this switching transition is stretched. And if you pay attention to the voltage and the current, they are the highest in this transition here, and therefore the MOSFET is dissipating its highest power during this transition. And therefore, the strong linear mode performance MOSFET is key. Now, how is this SOA or safe operating area is checked? There is in each MOSFET has a data sheet, and in the data sheet we provide a graph, which is what you see in front of you here, that has these lines. Now these lines are depending on the actual pulse subjected to the MOSFET. We start with the DC, meaning that if a MOSFET is being used as a voltage regulator, then it's the DC line that you need to look at. And the safe operating area is all the area below these lines. And the wider the area, the stronger the SOA performance of the MOSFET. Now, this is a standard technology MOSFET, which is designed or destined or intended for applications such as switching. It still has some kind of safe operating area, but the MOSFETs designed for a HotSwap application will have this safe operating area made much wider. And the wider it is, the stronger the SOA and the better performance it is for HotSwap type of application. Now at NextPeria, the actual technology itself does provide a strong SOA inherently with the technology it has. But there are specific devices that are engineered to give this strong, wide SOA performance. And the latest technology, I just took back here, by the way, this second slide on my right to the next slide. Although it is intended for HotSwap and wide SOA performance, the latest technology has been made even better and wider for that purpose. And I don't know whether you can see there is the line does have a kink at these end here. As you can see, it's not a straight line. Now these kinks, first of all, these lines refer to are based on a thermal impedance. Thermal impedance is the parameter that dictates how much power the device is allowed to dissipate. But at these ends here, those lines are not kept straight. And the reason for that is because thermal runaways occur and hot swap occurs, which then go away from adhering to the thermal impedance. The latest technology, not only it made the area wider, but it was engineered to get rid of these kinks and make the silicon, or make the device perform better than any previous wide area devices. Now, once you move away from the switching transition in the hot swap application, the MOSFET spends most of its life as a switch. Now it is fully enhanced, and for that, it needs to have the lowest RDS on as possible. What happens in electronics in general, and in particular with component, is that if you enhance an area in a device, it comes normally at a penalty or a trade-off of another area. And in this case here, if we make the MOSFET strong in its linear mode operation, it tends to come at the cost of having an RDS on wider or higher to what it normally is. While combining the two is very challenging, because what you want a MOSFET that is very strong in linear mode during the switching, but once it's fully enhanced, once it is fully switched, then you want a MOSFET, or the same MOSFET preferably, to have a very low RDS on. Now I'll go on in a moment and explain how NextPeria manages to kind of fit both in the same device. And that's the key thing about these technologies, is to always try to improve, and in enhancing one area, it comes at the trade-off of another area. We all the time are continuously looking at ways to get the improvement and get the best of both worlds. I get a bit more into details of what is involved in getting a performance, a wide or a good performance from in a linear mode operation, looking at the technology structure. I do appreciate that perhaps the audience is more accustomed to system level. What I'm trying to establish here is give an insight on the device that is fundamental to the module involved in supplying the power to the server boards. So hopefully with this in mind, that you will be able to move away from having a black box where things just happen in that black box, and having a bit more information on what's inside that black box, and be able to perhaps specify for your modules, for your design, a specific MOSFET for that application. The way I see the MOSFET role in this particular module is, in a way, the same as you see a microcontroller or microprocessor in a motherboard. And that's what I'm trying to hopefully establish from my presentation. Now, looking at the MOSFET itself, when it's in the package, it looks like this, but inside, the silicon itself looks like this. And if we were to take a cross section, this is a trench type MOSFET, and it comes as channels, and these are the drain, source, and gate, which is inside, how they look like inside a silicon. Now, what's involved in a linear mode? That is the characteristics, what we call a transfer curve. And what this means is that as you apply in a VGS, or applying a voltage across the gate on a MOSFET, as you're increasing that voltage, the MOSFET is allowing more current. Now, the characteristics of that switching is done between two temperatures. The MOSFET operates normally at 25 degrees, or the reference is 25 degrees, but it is capable of operating all the way to 175 degrees. Now, the reason we give two graphs here is to show how it behaves at different temperature. Now, With the same VGS, when the MOSFET heats up, it allows actually more current. Now this area is where the MOSFET is not stable, or the actual characteristics show that the linear mode is not stable, meaning that for a slight change in the VGS with the heat, then you have more current. Now it does cross a point, which is the ZTC point, which is the zero temperature coefficient, above which things get stable, meaning that the hotter it is, the less current you allow, and therefore you're not having an unstable situation where the current is out of control and it causes damage, which I'll explain in a moment. So going back to the cross section, now each of these cells is the equivalent of a MOSFET itself. Now, they are in parallel, and if one cell does allow current more than another cell, it will heat up more, and this will be shown in the next slide. So if a cell, which is a representation here as a MOSFET, does have a bit more current due to process or variation in the actual cell itself. Now, the more current it draws, the hotter it gets. And as I showed with the graph earlier, the hotter it gets, the less voltage it needs to draw more current. And it gets into this vicious cycle where it ends up with the thermal runaway, and it causes hotspot. Now, these hotspots will end up thermal runaways and will cause damage to the device. And this is what the damage looks like in a linear mode failure signature. As you can see, they tend to happen in a specific place, not the whole die, as you can see from here. And zooming in, it is quite a nasty damage, and the whole MOSFET is now no good. Now, how do we overcome those issues with the hotspots and thermal runaways? We look at the actual technology that NextPeria use, and it is called superjunction, as opposed to other trench structure. On the top here is what we refer to as a split gate. Now, I do appreciate that these terms may be too detailed for the system level designers, but a split gate just refers to the gate of the channel being split into gate and source, while the NextPeria superjunction hasn't got such a scheme, but it has what we call a superjunction. Now, the difference between the two, each one of them will have advantages and disadvantages. Now, for the SuperSOA and wide SOA, it comes down to the superjunction having the characteristics of the cell being wider, allowing more handling of the current without the compromise of the the RDS on being higher. Now, the RDS on lowering RDS on with the split gate technology is achieved by reducing the cell pitch, which you can afford to do with this type of technology, but that comes with the cost of the current handling being less effective as it would be for the superjunction. Now, to achieve a lower RDS on with the superjunction technology, now, there are some techniques, some clever techniques that are implemented, that are used, where the doping and the engineering of the actual cells is done so that you don't need to resort to lowering or thinning the cell pitch to achieve that. And the result is that with the wider cell pitch, then the current that you would normally get in a thinner or a narrower cell pitch being too much to handle is actually made better to handle, and therefore causing the making the actual silicon heat up less, and then ended up with the better performance in the SOA type of technology, SOA type of application. Combined with the actual package itself, the LF pack, which is a NextPeria flagship, package. This package here is a clip, copper clip, and it comes in one piece of source clip and one piece of drain tab, where the silicon is sandwiched between the two. This would provide a good thermal performance, which again helps with the current handling and keeping the silicon as cool as possible, which then would result in a good performance in the SOA. It has its advantages as well with the board level reliability, but that's a different topic. Again, compare this LF pack with what we call wire bond devices. The wire bond device will have a smaller area of contact between the actual wire or the pin and the die, meaning that there is a higher current density, which then would result in the current not being handled or the heat not being dissipated properly or as efficiently as it would do if you had the copper clip sitting on the die in a uniform way. That provides a uniform distribution of the current, which then will have a better or more efficient thermal performance, which will result in a very good and a better SOA performance. NextPeria itself is not a company from today. It's been going on since the 1920s and it's gone through various changes. And at one point it was Philips. It moved on to NXP, and 4 years ago it became NextPeria. NXP combines microcontrollers and other devices. NextPeria, the site in Manchester, focuses on MOSFET. And the expertise is developed in MOSFET particularly. But NextPeria as a whole does provide over 90 billion components discrete in the semiconductor world. That's an overview. It's a global company. And as I said, we have a branch in Europe, in Germany, and the division where I work for is based in Manchester. The devices that are available and are intended for HotSwap application are listed in this green section here. Now, it is important to pay attention to the actual device and its intended application. As I mentioned, some parameters are enhanced for particular application, while others are, again, optimized for others. The call to action slide here is that the huge amount of current, if it's not brought under control, it will cause damage. Now, bringing this under control is the obvious solution, but what's not so obvious is how it is performed and how it's done. I'm hoping by this presentation that it has given you an insight on how this is performed. The kind of support and services we would like to provide and be able to be of help are the MOSFETs samples that we can provide for testing. Now, the evaluation boards or reference design can be provided by the likes of ADI, which are very good with providing the module for providing a solution for HotSwap. And the links are provided as follows, as you can see here. NextPeria, as I said, for any MOSFETs, for evaluation samples, and any technical questions that you may have, please do not hesitate to contact us. And if you need any reference design regarding the actual module, and now that you know what's involved in a MOSFET, you can actually get these boards and try different MOSFETs. By that, I shall finish, and I hope it was useful, and I'm open for questions.
Hey, thanks, Sammy. That was probably the most detailed call to action I have seen, and it's been long since I've seen this much detail on MOSFET. So, thanks for sharing all that. Let me ask, Kaylee, okay, so she responded there are no questions from the chat. So let me open to the audience or anybody on the audio, if you guys have any question for Sammy. Okay, I do have one question, Sammy.
Sure.
So you did mention at the end you want to contribute to OCP and hardware management. I'm still not clear on, so what specific, what you're thinking of contribution here.
So yes, I mean, I had to think about this as to, I mean, I'd like to be able to provide any support possible and contribution that maybe, but it may be limited in a sense that we specialize in MOSFETs. Now, I do appreciate that this is not something that you normally used to, but what I can do is, in combination with these evaluation boards, I was hoping that our contribution would be in the different devices that we can supply, so that you can have a test, or you can see what is involved in supplying the power to these server boards that you may have. It may not necessarily be a straight away or straightforward knowing how these modules work to be able to actually implement them directly to your design, because you may not necessarily be involved in the design. But what it will do is it will give you a full understanding to perhaps come up with a specification in future where you actually have a say in what kind of MOSFET goes into the boards provided for you as a solution. Is the kind of contribution I'm hoping to be able to give.
Okay, thanks. Any other questions or comments? Okay, thanks, Sammy, for the presentation.
Thank you very much.
All right, we have a few minutes left before our next